starts now.
Good morning, everyone. So today it is my pleasure to introduce our speaker, Alexandre Solon, who is a CNRS researcher from Sorbonne University, specializing in non-equilibrium statistical mechanics and in particular in active matter. So Alexandre kindly agreed to present his recent results on collective properties in active particles. So Alexandre did his doctoral studies in Paris, University of Paris, Diderot, in 2015 in theoretical physics. Afterward, he moved to MIT, where he worked with Meran Kardar, again on active matter field. And from 2008, he's back to France, where he is a tenured CNRS researcher at Sorbonne University. So, and today he will speak to us about his recent exciting results on motility-induced phase separation. So one more formal announcement. We are recording this session, so please mute your camera, disconnect your camera and mute your microphone. And please, Alexandre.
Well, so good morning, everyone. And thank you, Mikola, for the introduction and for the invitation to talk to you today. I would much rather be with you in Lisbon, but well, that's how it is. And so as Mikola said, I'm going to talk about motility-induced phase separation. That's one type of phase transition that we find in active matter. It's maybe the simplest kind of phase transition that we have in active matter. But so first, since active matter is a relatively recent field, I don't expect that everybody is familiar with it. So I'm going to introduce a bit more generally what we call active matter. So active matter is made of active particle, and each particle is able to convert the energy that's stored in the environment into mechanical energy. So to be concrete, these particles consume some kind of fuel to self-propel, to move. So you find that at all scales in living systems. Inside your cells, you have filaments that are called cytoskeleton, which is what, like the skeleton of your cells, what gives them rigidity. And you have molecular motors, which are these molecules that consume molecules to work on these filaments and to exert forces. On a larger scale, the cells themselves or bacteria are able to move by consuming energy. And on a macroscopic scale, of course, most animals, including humans, are self-propelled particles in the cells. So active matter is made of many of these active particles. And I'm interested in statistical mechanics question. So given what you know of the behavior of one particle, say of one bird, what can you say of the collective behavior of the flock of birds? So these are some of the most typical collective behavior that you find in active matter. So of course, bird flocks. So we have all seen bird flocks, but it has been studied in detail by physicists, like tracking every bird in the flock. Here you have cell migration. I have the movie, so let me put it on. So you have tissues that can move around, invade new space, especially like tumors can move around a lot. And on the bottom, you have examples of two experiments with the filaments of the cytoskeleton and molecular motors. So on the left, you have actin filaments that make these waves of high density that are moving. And on the right, you have microtubule filaments, which when you put molecular motors, they form this that has been called active nematic, because it has a nematic symmetry. But you see that the defects are moving around the nucleate and the amylate. So it makes it an active nematic that's very different from what you have in your TV. So from the point of view of statistical mechanics, these are non-equilibrium systems that are characterized by a local drive. So each particle is driven differently, and that's as opposed to systems that are driven by an external field. So the example I've shown you are complex systems, biological systems, but as usual in the StatMech approach, we study simple models that we can understand more or less in detail, and we hope that there is some universalities, that these models will tell us something about the more complex system. And one thing that's nice for active matter compared to other kind of non-equilibrium system often, that we have many experiments that can be well controlled. For example, we can make artificial self-propelled particles, like these Janus colloids. So these Janus colloids have two faces with different properties. And for example, this one is coated with platinum on half of the surface. So when you put it in a solution of H2O2, it reacts with the platinum on one side that creates a gradient of concentration, and that propels the particle. But that's one of many ways to make artificial self-propelled particles. And the other very common kind of active particle you find in a lab are bacteria. And for bacteria, you have a lot of control using either genetic engineering or by selecting different mutants. And for example, in this experiment, they add a gene in the bacteria to get the interaction that they want between bacteria and to form these rings. So here's the outline of what I'm going to tell you now. So finally, I will tell you what we call motility-induced phase separation, or MIPS, and tell you in what model we observe it. And then I will show you that there are two levels of description for this transition. So first, using an effective thermodynamics, and then I will tell you about bubbly phase separation. So to be concrete, let me say precisely what kind of particle, what model I'm considering. So I have collections of active particles, and each one is self-propelled. That is, there is a force that's applied on it, and we take a force F with a constant magnitude. And the medium, we assume that there is dissipation. So either it's moving in a fluid or there is friction with a substrate. So the force just translates into a speed v. So we take a constant speed v. And then you need a mechanism to change the direction of this velocity. And you can have different possible mechanisms. So here on the left is called run and tumble particles. So they run in straight line, and then they completely randomize their direction at discrete time events. So that's more or less what bacteria like E. coli do. On the right is another mechanism, active Brownian particles, which reorient just with rotational diffusion. So that's what it's a model, a good model for the Janus colloid I've shown you before. But actually, for everything I will tell you today, you can forget about these differences. And the only thing that's important is that this particle is self-propelled with a characteristic scale, which is the persistence length of their motion. So that's the distance that they travel before they forget their orientation. So now let's consider many of these particles, and we just add a short-range steric repulsion. So these particles have a given radius, and they don't overlap. That's the model that has been studied by many people, the canonical model to observe MIPS. And so MIPS appears because of the following mechanism. So when you have two particles that encounter face to face, they are persistent, like I told you. So they are not going to bounce off each other. They will keep trying to move in the same direction for some time. And so actually they will get stuck one in front of the other and they will stop moving until one of them reorients and moves away. But if they get stuck long enough, other particles have time to come in and you make a bigger cluster. And so you have a feedback loop. Even more particles are going to come in. And in the end, what you get is a phase separation, where you have domains of high density where the particles cannot move, and domains of low density where they can move faster. So let me show you how it looks in a simulation. So I start from a homogeneous state, and at small time, many clusters are formed. And then you have a coarsening phase. So small cluster disappears, and you have larger, only the larger one remains. Until at the end, you have only two domains. You have a liquid, what I call a liquid high density domain, and a gas domain around it, and you have reached the steady state. So when you look at it, it looks a bit similar to a passive liquid-gas phase separation, but it's really a completely non-equilibrium phenomenon, because here you get phase separation without any attractive force. It's because you have self-propulsion and steric repulsion that you get this phase separation. So you see that the ingredients are rather simple, so you expect it to find it in different systems. And it has been observed in several experiments. Here I give some examples. So both for self-propelled colloids, here you have two different kinds of self-propelled colloids. And also for bacteria, here you have bacteria Mixococcus. So in each case, you have phase separation between a dense phase where particles move slowly or not at all, and a dilute phase where they can move fast. So the question I want to address for the rest of the talk is how to understand the phase coexistence in these systems. So we are out of equilibrium, so we don't have a free energy that we would minimize, and it gives us phase coexistence. You would tell us, for example, the densities in the two phases. Out of equilibrium, we don't have that. So what do we do? And so that brings me to my next part about effective thermodynamics. So what we would like is to understand the density in the system on a large scale by forgetting the little microscopic details. So what would we want is, starting from our microscopic model, to do a coarse graining to write an equation on a microscopic scale for the density field. But for the model I have shown you with the steric repulsion, we don't know how to do that. The interaction makes it difficult. And so one way to make progress is to use a different interaction. And so you can look at the model with quorum sensing interaction. So these are particles that move with a velocity v that depends on the local density rho. So concretely, in the simulation, each particle has a radius of interaction, and it counts the number of other particles inside, and it adapts its velocity according to a prescribed function v of rho. So this v of rho is an input of the model, and you want it to be a model of the slowdown that is due to collisions. So you take typically something that's decreasing with density. So for the simulation I will show you, we take this function, so a high velocity at low density and a low velocity at high density with a kind of step. But the precise form of this function is not very important. So in this model, with this interaction, we also have MIPS, and it's also similar to a liquid-gas phase separation. So let me show you how it looks. And here in this movie, I have two systems with the same parameters, except that the density is higher on the right. If you look on the left, you see that the homogeneous state is metastable, and at some point, you have nucleation that brings you to the phase separated state. So let me put it back. On the right, you see what's called Spinodal decomposition. So you form many clusters and they coarsen like in the previous movie. So these are also the two kinds of behavior that you have in a passive phase separation. So let me point that this quorum sensing interaction is an effective model for the collision, but it's also a real interaction that's used in some system, in particular bacteria that can release a chemical in the medium and sense the concentration of this chemical. So that is used to infer the concentration of bacteria around. And in this experiment, that's the kind of interaction that is used to make these high and low density rings that comes from MIPS also. And this model is also the first model in which MIPS was observed by Thayer and Kels back in 2008. But so now, since there is some averaging in the interaction radius, analytically it's easier, and we can do the coarse graining to write a microscopic equation for the density field by doing a gradient expansion. Well, it's a bit more complicated, but the point is that in the end we get a gradient expansion, and at the first non-trivial order in gradient, that's the equation that we get. So it's a conserved quantity, so you have a divergence in front. N is a mobility parameter, and then here you have mu naught, that's a chemical that plays the role of a chemical potential, and an interfacial term kappa. And we can express all these coefficients, relate them to the microscopic quantities. You don't need to look at these expressions. So for those who are familiar with it, you can recognize that it's almost a Candida equation. So the Candida equation is the canonical equation that you use to describe phase separation in passive system. And it looks like this. So you have divergence of m times the grad of a quantity mu. And mu is the derivative of a free energy with respect to density. And to be most generic, like in the spirit of a Landau expansion, you can expand the free energy as a local term, the free energy density, and the first gradient term, that is the surface tension. That's what gives you the cost of having an interface in your system. So if you do the derivative, this is what you get for mu. And you can compare that to what is here in the equation for the active system. So the local term is fine. You can always choose f prime so that it's the same as mu naught here. And we have the same term kappa Laplacian. But you see that here you have an additional term that's proportional to grad rho square. So all this to tell you that in the active case, you cannot write the chemical potential here as the derivative of a free energy. So this is not too surprising because out of equilibrium, we don't have a free energy. But then we need to generalize. It led us to generalize this Candida equation to include these terms that are not, that you cannot derive from a free energy. So we go one level below, and instead of expanding the free energy, we directly expand the chemical potential in gradients. And the most general expression that you have is this one with the local term and the two possible interfacial terms. So now our equation is a special case of this generalized Candida equation. So how do you understand the phase coexistence for this equation? So to make a long story short, if you use the usual thermodynamic construction, the common tangent construction or the Maxwell equal area construction, it doesn't work. But what we found out is that you can define generalized thermodynamic functions by doing a kind of change of variable and introducing an effective density, this R, that's a mapping to the real density rho. And it's defined as a solution of this equation that involves the interfacial term. So with this R, you can define a generalized free energy and pressure in the usual way, except that you have replaced the density. With these quantities, you can do the construction that we have learned in school. So you do the common tangent construction, and it gives you the two coexisting densities, so the R in the gas and in the liquid. And from that, you can infer the real density in the two phases. Or it's equivalent to also do the common tangent construction, the equal area construction on the pressure. So actually, it's similar to the passive case. Now that we have this function, we can determine the phase coexistence in the same way. There is one big difference between the two cases, is that now the phase coexistence depends on the interfacial term, because inside the definition of R, you have the interfacial term. And that's different from what you have in equilibrium, because you know that in equilibrium, the phase diagram is only controlled by the bulk. What happens at the interface doesn't matter at all. Here, on the contrary, the physics at the interface is important to understand the phase coexistence. So now that we can predict the coexisting densities with this construction, so does it work? Can we compare this to simulation of the model with quorum sensing? So I've shown you that we can derive the Coarsening equation. So we have all the coefficients. We can compute the effective density and get a prediction for the coexisting densities and compare that to what we measure in simulation. So here I plot the phase diagram as a function of density. And on the y-axis is the ratio of the velocities here in the two phases. So the different kinds of symbols are different types of simulations. So you have 1D, you have 2D, and you have Brownian tumble particles and active Brownian particles. And the theory is the red line here. So you see that it works very well, except at high velocity here. And you kind of expect it to break down because of the gradient expansion. To compare, the black line is what you would get if you in a sense, you pretend to be in equilibrium. That means that you throw away all the interfacial term in the equation. And you see that it performs much less well. So it's rather nice. We have a non-equilibrium model, a many-body model, on which we can predict analytically the phase diagram and to a good precision. But is it the end of the story, in the sense that is it also a good description of what happens in the original model, the one with steric repulsion, which is the model that most people are interested in? Actually, the big difference comes in when you look at finite size effects. So you consider now droplet of a finite size, and you can look at the pressure difference between the two phases. So if you do that in the model with quorum sensing, you compute this delta P, so it's the generalized pressure, as a function of the radius of the drop. You find that it's positive and it's decreasing as 1/r. So that's the usual result. It's the same in passive system. And it's this difference in pressure that drives the coarsening. So small bubbles have a higher pressure, and so they empty inside bigger bubbles. If you look at the same quantity for the model with steric repulsion, you actually find that this pressure difference is negative. So that has been interpreted as a negative surface tension and was first observed by Bjelke and collaborators in 2015. So it's rather surprising, because intuitively, when you think of negative surface tension, you have thermodynamics in mind. So you think it will be favorable to make more interface in the system, and so the system will be unstable. But what I've shown you at the beginning is a movie of a stable phase separation. So what happens there? And also, we have to see that this negative surface tension is not explained by the generalized Candida equation, which always gives you a positive pressure. So how do we understand this negative pressure difference? And what are its consequences? So that brings me to my third part about bubbly phase separation. Maybe if you have a few questions, I can take them here. Otherwise, at the end.
I have one. Can you hear me?
Yes, I can hear you.
Yeah, so you just mentioned that the system, you would expect the system to be unstable. Why? Can't you not have a non-equilibrium stable system with many interfaces? Well, yeah, stable, it's the definition of stable, perhaps.
No, I agree that you can have a non-equilibrium system that's stable. What I was saying is that our intuition comes mostly from equilibrium system, from which, if you have a negative surface tension, it is unstable. It will try to make interface everywhere in the system. But here, the meaning of surface tension is not the thermodynamic meaning, it's just the pressure difference. It's not a coefficient in the free energy. I hope that answers the question.
Yes, thank you.
Okay, so let me come to my last part about bubbly phase separation. So in this paper, Mike Cates and collaborators in 2018 introduced an even more general model that they call active model B+. In my language, it would be the even more generalized Candida equation. Very nice name. And So they realized that if you want to write the most general equation for a density field, you get this thing. So you, compared to what I have before, the m grad mu, you can have one additional term here in red that you cannot write as the gradient of a chemical potential. And they also had this last term, that's a noise term, to look at this equation in simulation. But so now with the red term here, for some sets of parameters, they observe negative surface tension. And the consequence is that they have reversed Oswald rippling. So what that means is that if you have two bubbles of different size, instead of the small one disappearing and the big one getting bigger, it's the opposite that happens. They tend to equilibrate their radius. And if you look at the simulation of the equation now with noise, what you get is this kind of behavior. So you still have a phase separation, sorry. You still have a phase separation between a gas and a liquid, but inside the liquid, you have bubbles of gas. And these bubbles have rather complex dynamics. They get nucleated, they move around. Sorry, it's my mouse. They move around, they merge, and ultimately they get expelled inside the gas. So that's what they have called a bubbly phase separation. But so that comes from the equation, but now is it really what happens in the microscopic model? Because in the movie I've shown you in the beginning, we didn't seem to see any bubbles. But actually the recent work that we did is to recognize that, yes, in the microscopic model, you generically see these bubbles, but you need very large systems to see them. Here is an image of what you get when you have 1.6 billion particles. So it's rather inconvenient if you want to study these bubbles because you need very large systems, and also you need very long simulation because the time scales for these bubbles to move are very large. So what we did is to introduce a lattice model that has the same ingredients. So the particles are self-propelled. There is some isotropic diffusion, and with some rate, the particles reorient to another direction on the lattice. And the excluded volume is just that you cannot have two particles on the same lattice site. And we take this kind of hexagonal lattice. With this lattice model, you see the same phenomenology for the bubbles, but numerically it's much more efficient. So we can look at large systems and really study quantitatively these bubbles. So in particular, we measured the number of bubbles of a given area A. And what you see is that there is a power law distribution with a cutoff that increases with the system size. So our interpretation of that is that this bubbly liquid has all the properties of a self-organized critical system. So you know that the canonical model for self-organized criticality is a sand pile with open boundaries. And here, what plays the role of the grain of sand that you add to the pile is new bubbles that gets nucleated. And the open boundaries is just the outside gas. And then you have avalanches of all sizes with a power law distribution, which are these bubbles. That are at all sizes. And let me show you the movie that I forgot. So that's how it looks like in a simulation. So it goes very fast because you have very different time scale. The big bubbles go rather slowly, and the small ones go much faster. And you see that sometimes you get very large bubbles that gets in the end expelled in the gas outside. Let me play it again. Okay, so we have this self-organized critical state. Let me show you a minimal model that contain only the important ingredient to understand this, to understand better this state. And we call it a bubble model because now the degrees of freedom are directly the bubbles, and they have a radius, a varying radius. And to implement the reverse Oswald ripening in a minimal way, what we do is that we nucleate new small bubbles at a constant rate, but the total area of gas and liquid is fixed. That's also something that's true in the experiment, in the simulation, I mean. So when you nucleate small bubbles, you do it at the expense of bigger ones. And then the bubbles diffuse and they merge. And only with this ingredient, you recover the same type of phenomenology for the bubbles. Here's what it looks like in this radius, in this bubble model. You also get bubbles at all sizes. And now, of course, we can have very large systems and compute the same quantity, the distribution of the bubbles depending on their area. And we also see that it's a power law distribution with a cutoff that increases with system size. And here it's collapsed because it's rescaled by the system size to some power gamma. And so actually, in this state, you have two critical exponents that are here the decay exponent and the exponent controlling the cutoff. Okay, so I'm already at my conclusion. I guess I'm a little early, but we'll give more space to discussion after. So to summarize, maybe give you my understanding of this phase separation, that there are, as I was saying, two levels of description. So even when you have bubbles, you still have a phase separation between a liquid and a gas with well-defined densities. And this part is well understood using the generalized Candida Equation, which tells you that it's more or less like a passive phase separation, except that the interface is important. And the second step is that you have negative surface tension, in the sense that the pressure difference in a drop is negative, and that gives you reverse Oswald ripening and ultimately this bubbly phase separation. So this bubbly phase is something that's been discovered very recently, and there are still many things that we don't understand. For example, I've told you about these two critical exponents. We don't know if they are universal, or we don't know how we could compute them, how they are determined. And another question for the future, more for experimentalists, is to see if we could observe in an experiment MIPS with bubbly phase separation. which is not the case so far. So I want to acknowledge that it's a very collective work with many collaborators over the years. And so I let you read their name, and I thank you for your attention. And I'll be happy to answer all the questions.
Okay, thank you, Alexander, for this nice talk. So now we have plenty of time for discussions. Who has a question, please go ahead and ask. Okay, so
I have lots of questions, but I suppose maybe I can let some of you start.
I have a question.
By the way, I can put my video. Alexander, thank you very much for your talk. Very, very clear.
Thank you.
But I'll probably I've been studying your work and Kate's and so on, and I have a few questions, but maybe I'll let the others start, and then I'll ask some of the difficult questions for me. Anyway, in the end, if they don't ask any questions, then I can go ahead.
I have a question. Do you have the bubbly phase for all values of activity in your model inside the coexistion?
In this model, well, the real answer will be we don't know. But for all the values where we see a clear phase separation, we get these bubbles. What is not clear is what happened close to the critical point at just at the activity at the onset of the phase transition. But otherwise, in all the phase diagram and in all the parameters that have been studied in the literature, you have these bubbles. Yes.
Okay, so I have another question. The alpha exponent on your power law is the same for this model and the bubble model that you tested?
It's not very far, and at the precision that we have is the same, but we still think that it's not universal because in the bubble models you can change this parameter by changing some details of the model. For example, you can change how the bubbles diffuse depending on their size, and that will change. It seems to change the critical exponent, but that's still something that's ongoing work. And it's not very clear at the moment.
Okay, thank you.
I have a question, if I can.
Yes, go ahead, Danny.
Yeah, so I wondered, and I guess it's a very difficult thing to just observe experimentally, but is there any such thing as MIPS in biological systems? We've got, of course, many more impurities and variables, but is there such a thing observed as MIPS in biological systems?
Biological systems are always more complicated than my little models, so we agree on that.
That's
But I think there is MIPS, or at least MIPS is important in some phenomenon, like this example that I gave. It's MIPS, but the difference is that these bacteria they reproduce, they die and they divide, and that gives you a ring pattern. But the mechanism to form the one ring is MIPS, and it's really because this velocity decreases with density.
Yeah, and if you were to go farther, so if you go to the, I have two questions there. One is if you would look at the time scale at which they don't die, whether you what you would expect, and whether you, and the second one is what I'm really trying to get at, is this in somehow, is this sort of an evolutionary part behind this? Like, does it have some advantages for systems to do this? And is this, if you go back a few steps, does this lead to the creation of more complicated organisms, for example, when you've got a lot of different systems interacting with each other, trying to, or effectively they're not merging, but if you're thinking of cells, I imagine that's possible for different kinds of cells to start merging, right? Or anything like this. And it could be driven by a system like this, which therefore might play a role in evolution. But I've never read anything about it, but it could be, I guess.
That's a very interesting topic on which I'm really not a specialist. But what I can say that in this experiment, so it's not really a natural system because they add the interaction by hand, but it's a way to model to control the kind of this quorum sensing interaction that you expect to find in bacterial systems or maybe in cells. And so that's like maybe one of the maybe generic properties that you would expect, because it's I guess the simplest interaction that they could have.
Yeah, so maybe we hear more about this in, let's say, 10 years.
Yeah.
Okay, Nuno.
Hi, Alexander. Thank you very much for your talk. I have several questions, but regarding since you have this slide, I will start from the quorum sensing model. All these models with a velocity that depends on the density differ from the models that where you have diffusion that depends on the density. Are they significantly different?
If you have only diffusion, so the models, the physical models where you have only diffusion that depends on density, the thing is that the diffusion is always positive. The big difference here, I think, is that the velocity enters in a different way inside these coefficients, which can make them negative, and that's what will give you the phase separation. So that would be the big difference. But if you have a model where you can have negative diffusion, maybe it's not so different from what.
Another thing is that you when you do this mechanistic description at the beginning, you really focus on directionality, but then your continuum model has no directionality in it, right? And I find surprising that when you show your diagram, you say, oh, interfacial terms are important, but then you look to the interfaces that you get with these models, and they are very different from the ones you show in the beginning with your simulations where you had a very rough interface, isn't it? If interface is important, why two models with completely different interfaces are able to get a good quantitative agreement?
Well, I mean, maybe, to be clearer, the two models are very different because of their interface. In this, you are right when you say that they are rougher in the original model with steric interaction. That's also because of this negative surface tension.
Yeah, but in this diagram, you don't have that into account. And
You do. Of course you do.
no, but the shape of the interface with this model is very soft and very smooth.
I think my question is simpler. I think I want to go next.
Well, okay, if you want to interrupt me, feel free. Okay, good.
No, but
No, it's okay.
well, I enjoyed Alexandre recalled it surface tension. I don't know, Mike Cates doesn't like it, but I also understand it like that. And sometimes it causes confusion. So the first thing I would like you to clarify, and a question has already been asked, I think for quorum sensing particles, you never get the negative, let's call it surface tension, the interface, the gradient, the coefficient of the gradient term,
Yeah,
right?
Right, that's right.
So that's why you don't get MEP, or you don't get the bubbly phases, or you don't get any. And in the active Brownian particles, on the other hand, as far as I understand from the literature, you always get a negative term, right?
That's right. Yes.
Even if you call it surface tension. Mike is not listening to us, so let's call it surface tension. So I think those, you and I understand what we're talking about. Maybe this is not a surface tension, maybe nobody knows what the surface tension is, but it's the coefficient of the gradient terms that
That's it. Yes, that's what it is.
Fine, so we're on the same level. So quorum sensing, boring, blah, 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 and you know, active Brownian, exciting, strange, not really quite understood. Now, leave that on that same slide you have on. Can you tell me, the coexistence curve is not symmetric, as it would not be for a liquid vapor. But in some of the effective models, like the active B and so on, yeah, they are symmetric. Any consequences that you think of? I mean, let me clarify. I mean, in your paper, you claim that there is this bubbly phase in the liquid phase, but not in the gas phase. Is this just because the time scales are very different? Or is it because there is something intrinsically different that comes from the symmetry, which is broken in the model, but not in the effective model?
So you're right that when they look at active model B, model B, they have a symmetric potential. So there is a symmetry between gas and liquid. In the microscopic model, there is no such symmetry. So you don't have any symmetry between.
So you only see bubbly liquids. You've never seen gases with droplet gas phase.
Not in microscopic models, no.
Not in microscopic models. Although these model would predict them, but because it's based on this symmetry, which probably is broken.
Yes, and it would be interesting if we could find a model that shows the opposite.
In the Lattice model, you almost seem to have a symmetric phase coexistence, unlike for the active Brownians, at least the one we did. It looks very symmetric, but we could never really prove that it is symmetric, and maybe the asymmetry is not. I'm just talking about the binodal. The binodal in your Lattice model, which is very similar to something we used, the phase diagram looks very, very symmetric. Well, we use a square lattice, not an hexagonal one, but I don't think that would make any difference. If we plot the binodal for this model, well, for the one we did, it looks very symmetric. So somewhat different from the one you have for the quorum sensing, well, for the plot defective thermodynamic. But I was always a little bit suspicious that there was some asymmetry, although it's difficult to pin down on this model where it comes from. But
yeah, I don't know about that. Yeah.
I mean, a hole is not really the same as a particle. The particle has the velocity and the hole doesn't. This is the only way I can understand it, because if this were passive, it would be a completely symmetric whole particle system. Oh yeah, do you have any thoughts on that, or am I just being stupid? Or
I think you know more than me on this topic. I would not expect a symmetric binodal for the reason that you said that hole and particles are different.
Okay, well, final question. That's the another thing that happens when you have a negative tension. You know, you might have different phases, and of course, not in the lattice. You don't have solids, but I'm sure you know about the recent PRL, Geisler. He says that in the MIPS region, he finds a solid. Can you comment on that?
Well, it depends on the interaction, yes.
Yeah, well, not in the lattice. In the lattice, you don't have a solid, as far as I understand. I mean, you cannot have a solid, really, because the positions are set by the lattice, so it's very difficult.
Yes, or maybe you cannot have a liquid.
Well, you call it liquid. At least we do for 40 years, and we're all, you know, like we call.
I'm fine with calling it liquid. So you also have a transition between solid and liquid. If you look at active Brownian particles, that depends on how stiff the potential is.
But not on the lattice, just for the continuum.
I agree. No, in the lattice, nothing seems
I don't
to.
think in the lattice. I mean, unless it is active. Thank you very much. Very beautiful talk. Lots of questions to be answered, and yeah, I'll be in touch. I've been following your work and others.
Great.
So, Nuno, can you continue your question? You had to.
Sure. I'm sorry I interrupted.
It's okay. I go to the second part because I have several questions about the second part, but I will try to do only one or two. The first thing is I don't really understand why you call it self-organized criticality.
Ah, yes, it's a touchy subject, I would say. To me, it's very similar when you think about it to these senpai models. In a way that you have the separation of time scale, that is you input small droplets at a low rate, they come from large fluctuations. You have the open boundaries. And what's interesting is that they are not imposed externally, they just come out of the phase separation. But the outside gate phase plays the role of open boundary. And then, so you have this bubble dynamics that gives you bubbles of all sizes. And when they get expelled, you can see that as an avalanche in the sand pile. So to me, the analogy is rather.
But where is the avalanche? This is what I could not understand. I don't see any avalanche dynamics there, right?
Well, for example, a plot that I don't.
The image is broken.
I think we've lost connection, no?
The connection problem.
That's let me send email to Alexandre. Maybe. Sometimes the speaker can continue and.
Maybe he's coming back.
Okay, yeah.
Okay, sorry.
Welcome back.
Let me share the slides again. I'm not sure until where you heard me.
You were just starting when to answer.
So I think I was saying there's one more common point between this model and the self-organized criticality in sand piles. Mm-hmm. That if you increase density here until there is no more gas outside, you lose the criticality.
It's okay, but I don't see is where the avalanches are.
So the avalanches, maybe you didn't hear that part. I was saying that you can look, for example, at the total area of bubbles inside the liquid as a function of time. Mm-hmm. If you do that, you have large peaks that you can call avalanches that corresponds to when a bubble exits, and you have bubbles of all sizes. So you get these peaks. I mean, it's not an avalanche like in a sand pile, but it has the same role in the dynamics.
Yeah, but the key ingredients to self-organization is slow driving.
Yes.
and some redistribution or either mass or energy or whatsoever. And this is what I don't see here. So
the way I understand it is that the slow driving is the input of new bubbles.
this is okay, yeah, but then you don't have really redistribution of energy and relaxation and threshold values. Anyway,
You have a distribution of the bubble area because of the reversals of rippling.
no, but the redistribution is not, well, anyway, it's okay.
Right.
So another question is, what is the value of the exponent?
Also, I don't want to get it wrong. I think alpha is around 1.5 and gamma around 1.7.
Okay.
Uh,
Also very different from the ones of Salk in 2D, right? But anyway, it's okay. Good.
Yeah.
Okay, thank you. Thank you very much, and
Yeah,
nice
my
talk.
pleasure.
Cristobal, please.
Okay, so I have another question. Did you measure the time scale of diffusion of your bubbles or the survival time scale of the bubbles in your model?
Yes, we have tried to measure that. It's not very easy, but
Yeah.
Because it's something important when you model it also, like how quickly these bubbles diffuse as a function of their radius.
Okay.
And it seems that the diffusion coefficient goes like 1 over radius. I don't know if it's what we expect. We don't have an explanation for that. But
Okay.
maybe it's not exactly your question.
I was trying to sometime compare with the time scale for the formation of the liquid phase, and now the time scale for the survival of the droplets compared to the time scale for the formation of the liquid phase.
Mm-hmm. There's something else that's interesting, is the coarsening of the droplets. So for the liquid is the regular coarsening law. So if you start from something homogeneous, you nucleate liquid everywhere, and the typical liquid size will grow as time to the power 1/3, like you expect for normal phase separation. But if you look at how the bubbles coarsen in time, it goes slower as t to the power 0.2, maybe 1/5. And we also don't have an explanation for it.
Okay.
So the bubbles coarsen slower than the liquid.
Okay, thank you.
Any more questions? I can have one.
Last one.
Margarita, okay, go ahead.
One, and you've already noticed that there are two communities. One is the dynamics, the other one is the effective or the thermodynamic one. If you go back to your phase diagram in the effective thermodynamics or effective, right.
Yeah.
So the green curve here is active Brownian particles, right?
Yes.
So this should be a bubbly liquid, right? Not a liquid vapor.
Okay, no. It's active Brownian particles in the sense that their velocity is reoriented by rotational diffusion, but it's still the quorum sensing interaction.
Okay.
Sorry for the confusion.
No. I was just wondering that perhaps this would be a finite size effect. So if you look at active Brownian particles in small systems, you see just what looks like, let me call it simple MIPS. But if you say the interactions are really different, then so all of these would be quorum sensing particles, right?
Yes. Yes, yes.
It's not a finite size or anything. Okay. Thank you.
Alexander,
Finite size or very small system phase diagram, we just see, I mean, we're not looking up for the bubbly liquids. We just see something that looks very much like a binodal.
Oh yeah, the phase diagram looks similar. Even with the bubbly liquid, because even when you have the bubbles, you can still measure the coexisting densities and plot this phase diagram, and it looks similar. It's just that we don't plot them on the same one because it's not the same parameters, but it has the same shape.
It has the same shape, but I understood that ultimately, maybe I'm wrong, ultimately the bubbly liquid would just use up all the vapor into the liquid, so there would not be a diagram like that. It would be just like a microphase in my equilibrium language. It would be like
you're right. Something I didn't come to that level of details, but actually, yes, you would. We think that for very, very large system, well, you could still plot the binodal, but in the middle, it would not be phase separated, but microphase separated. Yes.
But then but in the middle, it's microphase separated, so the binodal would just be some sort of metastable. I don't know.
The binodal would still be the density in the bubbles and in the liquid.
Oh, I see. I see. But there wouldn't be a bulk liquid vapor separation, right?
No, yeah, that would be the difference.
Everything would be bubbly.
Yes.
So everything would be like, yeah. I mean, nobody in equilibrium would plot a diagram like that if you had just a phase that is inhomogeneous with liquid and vapor, but there would not be a bulk liquid vapor as far as at least from.
Well, on the left of the binodal, you would get a bulk vapor, and on the right, a bulk liquid. Just in the middle, you would get the phase separated, the microphase separated. Sorry.
Yeah, but the bulk liquid, if I understand, would never coexist with the bulk vapor, right?
No, only through microphase separation.
No, it's just I'm trying to. Sometimes it's difficult to read in between what you write in the papers, but this is what I understood. I was just trying to make sure that.
No, that's all correct. Yeah.
Thank you, thank you. Okay.
So maybe I can ask last question. So do you understand correctly that active Brownian particles with repulsion exhibit always reverse post-Wald typing in the terminology of my case, the paper here X08, right? So active Brownian particle, repulsive, always bubbly liquid, right?
Yes. No, it's not clear why it always falls in this or in this behavior, because in the equations they have regions where they don't have the bubbly liquid.
Right. And if you add a weak repulsion, attraction, I mean weak soft attraction, does it change? Do you expect something?
If you have a weak
active Brownian particles with short attraction, or with some.
I don't know.
Yeah. You don't know. Okay.
No, I don't know.
Okay. So I don't, Margarita, please.
I think that the region where they don't see bubbly in the B plus model, when they don't see the bubbly phase, is when the surface tension in my language, which Mike does not like, when the surface tension is positive. Because of course, if you have this general model, you can find regions of phase space where the activity is such that the combination of those parameters will give you a positive delta P or whatever, a positive surface tension. In those regions, of course, there is no bubbly separation. But active Brownian particles, from what I understand, now going to the microscopic model, I mean, then it's no proof, but I mean, all the models that have been studied, they have this negative tension. So the activity parameters there would fall into the region for the B plus model, where that delta P has the wrong sign compared to the what we used to, and so they would fall into this bubbly. For the gas side, to me, I think it's either a very different time scales, or maybe there is something really different in the microscopic models, but I don't know. I don't understand it.
Yeah, I agree with all of this. One thing I don't know is that, as you suggest, if we change the model, put some attraction, we have no arguments to say if the surface tension would still be negative or positive. We don't really understand in the first place why the.
Well, some people even object to calling it surface tension, but yeah, it's the parameter that controls these bubbles.
The pressure jump.
Pressure, yeah. But yeah, interesting, very interesting. I think it's still probably we still have lots of surprises, but because the other thing that they were hinting at, Cristóbal and Nuno, is that these interfaces are also very strange and very. We'll try and look at them, but we haven't looked at them properly. But they also have a very strange scaling behavior. It cannot be the equilibrium one. Not for the static ones. It cannot be. It cannot be capillary waves, and for the growing ones, God knows. But I think the interfaces will also be very different. But we don't have a general model, and the simulations know from the bulk. I mean, the simulations seem to be dependent on your time and length of the system. So just doing it numerically might be without some guidance. But yeah, I'm sure the interfaces are very different. What I've seen published by Marchetti and Lowen and so on is that it looks like capillary waves, the 1 over q squared. It cannot be.
I agree. It's not clear.
It's certainly not clear. It's not true.
No.
2 point something. But anyway, if we don't know any better, you call it capillary waves. But it probably, this is for the static ones. Now, if they're growing, God knows what it is. KPZ, QKPZ, God knows. We were trying to think about that, but when we saw your paper and the times and the lengths of your systems, the size of your systems, we got really scared.
Yes.
We have a very nice trick in the paper that we've, because we've been looking at just absorption and wetting and so on, and we wanted to keep the bulk density fixed. So we invented some sort of mechanism to feed in particles into the system, which is not an ensemble because you cannot prove anything out of equilibrium that there are ensembles. But we have not really understood the interfacial roughening. We think we can have, well, maybe. But yeah, I'm a bit scared. It depends too much on the size of the system. So difficult questions, but interesting ones. I don't think it can go back to all the effective thermodynamic scaling or non-equilibrium scaling, but God knows what it is. But yeah, very interesting. And the solid, I was also, I mean, I haven't studied the paper. If it's a solid rather than the lattice model is what you've seen. I mean, that my experience from lattice models is what you've seen. If you just have the continuum model and they crystallize, well, then it's something else. But who knows? Interesting.
Yeah, there is an interesting paper also by Cugliandolo and collaborators.
By whom?
Laetitia Cugliandolo.
Oh yes, but I haven't seen that.
And
Maybe.
it's also in the regime where it's crystallized, and there are domains of grains of crystals that also have an interest in dynamics. So it gets more complex once you have a crystal.
Yeah, I know. We always try to avoid crystals, but you know, life sometimes crystallizes. And I'm sure the same will happen for these active models. So it's an extra type of order that maybe you have to worry about. Thank you. It was a very interesting talk, and I think you've clarified some of my questions.
All right, great.
I'm pretty sure we'll see new results in the coming years.
Thank you, Alexander. I think we have a lot of questions, so it's time to thank Alexander again.
Well, thank you very much. And hope to see you someday in Lisbon, maybe.
Yes, sure.
Thank you.
Now people can travel for tourism, so they can travel. Well,
Science.
this was only this week, so
Yeah, it's very reasonable.
let's see how it works. Maybe next year we can do some traveling. Maybe you can visit us. Your seminar, it was very interesting and very we trying to do something on the interfaces rather than, but now, you know, all this bulk, you cannot look at the interfaces if you don't understand the bulk, and so this is how I'm educated. Whether surface tension or anything else, fluctuation as the interface, if the bulk is not understood, you know, we just but anyway, it's interesting. I'm very interested. That does not mean I know anything about it or I know how to proceed, but at least it interests me, which is thank you.
Well, thank you for your interest.
Thank you again. I think
Thank you.
Paolo,
Thank you.
Paolo, I think you can now stop recording, right?
Okay, so we'll be back next week. Recording stops now.